Okay, hi everybody. It's the evening lectures I've promised to keep. If you read my abstract, I've promised to keep the maths down. And so we want to keep it light but get the idea. And it's okay if I don't complete my talk, so please keep interrupting me. Like, let's have questions at any time. You can just either start talking or show your hand. Okay? Yeah, so Sumathi said, I'll tell you a bit about my background and how I got into this. So there's only one point I want to make here, which is that when I was maybe in high school, I just didn't even know like what I wanted to do. I knew that in school, the only subject I liked was maths. Science was not a subject I particularly liked. And then I just followed the route of, doing the best thing that your rank will fetch you, or so-called best thing. So like I followed that kind of route, and I did not want to do, I did engineering. I did not want to do research at all. So like I wanted to do a job. And after many years of not being able to do something which I like to do, then at the age of 29, I started a PhD. So that's when I decided I will come into academia. So the point I want to make here is that sometimes, until you live a thing or until you do a thing, you don't know whether you like it or not. And one option is like, suppose you got into a job and then you're working for a few years and then you think, oh, it's too late now to do anything about it. I'm in this thing. And then you do something which is not something you really like, but then you're doing it because you did it for the last 5 years. I think that's not a good idea. I'm telling from my personal thing. It may not, it may be a good idea for others. But so that's one thing that you can, if you really feel very happy about something, like take it up bravely. And it will work out if you really, really enjoy it. So, and I did a PhD, though I didn't want, but slowly I started liking fluid mechanics. And now I'm very, very happy that I did this as a career. So, any questions on that? Okay, so let's talk a bit about fluid mechanics. So, fluid mechanics is a very, very vast subject. It goes from, understanding how germs swim, like, how viruses attack, and it goes all the way to how galaxies form. So, there is fluid mechanics on every scale, and it's a very, very important subject. But I'm only going to talk about this particular small window of fluid mech, which is interesting me at present. It's one of the things I'm studying at present. And it is called particulate flows. And we'll talk about a few other things as well. How many of you studied at least one course in fluid mech? 1, 2, 3, 4. Yeah, few of you have studied a course in fluid mech. And how many of you studied something in your 12th in fluid mech? Everybody studied something. Okay, great. We'll start from there. So when I say particulate flows, I mean dusty flows. And in dust, I'm also including little water droplets. So I'm including also a cloud as a dusty flow because it contains tiny water droplets, which I'm going to think of as solid particles. They behave basically like solid particles. So here are a lot of examples. They're just a few of the total number of dusty flows, which occur in the atmosphere and in industry and in the ocean, many places. So anybody has a question about what any of these is? What? Can you talk loud? Prilling. Okay, prilling is a thing that they do to fertilizers. So like you make a liquid fertilizer and then you're going to make it into tiny little particles. So like you pour the liquid from a very tall tower like this one, and then like you put hot air from below. So as this thing comes down, it solidifies. Okay, and you can make powders also like this, like baby milk powder. So many things are made by these processes. So these are all particulate flows, and in all of them, there is turbulence. That's the common thing that I want to bring out. So yeah, how many of you have an idea what what? Turbidity current. Okay. So basically, like when a river, there's like when a river flows, it collects mud along its way. And then, like, interestingly, it's actually interesting because a river contains usually fresh water. And when it comes to the ocean has salt water. So technically, the river water is lighter than the salt water. So it should flow on top, not in the bottom. But because it contains so much mud very often, mud, sand, then the net thing is heavier. So it starts sinking. So then it forms this kind of current at the ocean floor, which then proceeds. So then these can make underwater sand dunes, many interesting things. So if you saw in our lab, there's a sand dune experiment. So if you guys go to the lab tomorrow, just ask Iqbal or someone to show it to you. Yes. Dusty flow means a flow in which there are solid particles. That's all. So like in many of these examples, there's air and then there's a lot of dust particles or solid particles. So these are all examples of that. It could be inside water also. Yeah. Dusty flow doesn't mean turbulent, but most flows are turbulent. Most big flows are turbulent. So we're coming to the word turbulence now. How many of you have an idea what it is? Yeah, tell me, what do you think it is? From? Okay. Okay, yeah, that's correct. Like the Reynolds number is an indication of whether it's turbulent or not. We'll be talking quite a lot about the Reynolds number. But like, what do you believe is turbulence? Like, if you see it, will you know it? I'll give you an exercise for all of you. Just after this class or whenever you have time, go on the internet and try to see like what is above our heads, like what is the flow above our heads right now. Okay, so like all of us, our body temperature is what, like 98 something, right? And what's the room temperature? It's less, right? We, like body temperature in centigrade is 37 and this room may be 25, something like that. So then like we are actually hot engines, all of us. Like we've eaten a lot of food and all of us are hot engines. And because like we are so hot, like warm air rises above our heads all the time. We're not seeing it right now because it's transparent. But this air is already turbulent. So if you look above me, there'll be this heavy vertical flow and above you also. So yeah, that is what it is. So almost any flow you see is turbulent. You wanted to say something? Okay, so now the point is, what is turbulence? It's like something very, very counterintuitive. And that's why I want to spend a few minutes talking about it. So like, what do Newton's laws tell you? Like force equal to mass into acceleration, right? And then like, if I put a force in this direction, you expect the body to accelerate in this direction, right? If I'm applying a force and it's a vectorial equation, right? So if I apply a force in this direction, do you expect the particle to go that way? No, right? Except in fluid, that's exactly what happens. So like suppose I take a pipe, that's why it's counterintuitive and we'll see why it happens. It's not disobeying Newton's laws or something. So like you take a pipe, okay, and I put high pressure here and low pressure here. And I pump a fluid through, right? Then like which direction am I applying force in? This direction, right? So the flow, the fluid should move like this. Agree or disagree? Agree. But then in most of the pipes, like she said, Reynolds number is just a measure of how big the flow is. That's a simple way to, how big and fast the flow is. That's one simple way of thinking of it. It's velocity times length or some radius divided by kinematic viscosity. So if it's fast and big, then the Reynolds number is high. Viscosity is low and these things are big. If the Reynolds number is reasonably high and there's no golden number, then what happens is instead of going like this, they go in arbitrary directions, all the fluid particles. Why do you think that happens, and why do you think that's still okay with Newton's laws? So like right now I told you, this plume is rising above my head. I mean, I'm hotter, so the air above me is lighter. It should walk in a straight line upwards, right? Instead of which it does all this. Like gravitational force should act directly upwards on a light thing. Any thoughts? Yes. No, it's not third law. It's second law only. So the interesting thing is that there is this thing called pressure. And pressure can redistribute force in funny ways. And so like just because the average pressure is high here and low here, it doesn't mean that's the same everywhere. You could have high pressure here and low pressure there. So you could have flow going in that direction. So the pressure field is a very interesting thing which redistributes. So second law is still obeyed. So the interesting thing is that, I'm creating things which should go in straight line, but I'm getting all these very complicated motions, very chaotic motions, which actually dissipate a lot of energy. So it's actually wasteful. Like when I'm trying to push it from one end to the other, if it would walk in a straight line, I would have to spend less electricity to pump it. But now I spend more. We can't help it. It's always turbulent. And in these big, big flows, everything is always turbulent. So that's why you see like this thing, you see this vorticity, right? Like you see this rotational motion everywhere in this pollutant rising and in any of these flows. We'll come to marine snow in some detail now. But yeah, and the way I put it, it looks like turbulence is all bad, right? But sometimes turbulence is good also. For example, like in the washing machine. So typically, what does a washing machine have? It has some rotating drum, right? It's either rotating this way or rotating this way, correct? So like I'm putting energy in this scale and I'm giving it. Now suppose the water inside the washing machine did not do turbulence. So that then it will just go in solid body rotation, agreed? It will just go in solid body rotation. So then like, suppose I put soap here and clothes here, the soap will do this and the clothes will do that. They'll never see each other, right? Whereas like I'm putting solid body rotation like this and I'm getting vorticity in all directions of all sizes. So now the soap and the clothes are mixing very well and they're meeting each other and becoming clean. So like I'm getting vortices of all sizes, and this is called turbulent cascade. So you have like energy pumped into this scale and it's going into smaller and smaller scales. The vortices are smaller and smaller. And then the very small scales get dissipated. Yeah? Where else do you see turbulence in every day? Can I elaborate vorticity? Yes, I can. So like if I take the velocity anywhere, who asked this question? Yeah. So if I take velocity at a certain place, velocity is a function of space and time, right? I mean by x, I mean a vector. Now, if I take the curl of this object, that's called the vorticity. Okay? So like if a fluid is in solid body rotation, I'll get a certain vorticity. The vorticity will be twice of the angular velocity. You can actually calculate this. And if it's not in solid body rotation, still I'll see like rotational motion. So like although I'm putting fluid in a straight line, I think it's giving me rotational motion everywhere. And if you look at turbulence, so like if you look at something like this, we'll see it in the next photo. You'll see these, long snake-like, noodle-like structures into which the vorticity is concentrated. So inside that, it will be rotating fast, and outside that, it won't be vertical. The curl will be zero outside that. So a lot of interesting things, like a lot of interesting reorganizations happen. That's why when somebody says turbulent, it's just random motion. It's random, but it's not like white noise. It's organized motion on different scales. So a lot of interesting things are there in turbulence. Yeah. Any other questions? Yes. Turbulence is an example of a chaotic motion, but all chaos is not turbulence. Turbulence is chaotic, but chaos doesn't mean turbulence. I can get chaos in population dynamics. I can get chaos in many, many other situations, like in electrical circuits. Okay? So those are all not turbulence. Chaos just means unpredictable motion, which is not repeatable. There's certain definitions of chaotic motion. Where do you hear the word turbulence? Aeroplane, right? And that's very interesting because like next time you guys please take window seat, and if they say like wear your seat belt, we're going to face turbulence, look out of the window and you'll see clouds. You'll be flying through clouds. So clouds are usually turbulent, especially monsoon. That's why it's so difficult to fly in the monsoon season, no? Because you have hugely turbulent clouds. And yeah, so they are an example that we face. So there is also clear air turbulence, but that's rarer. Usually when they say wear your seatbelt, it's because you're in a cloud. Okay, so we'll talk about marine snow. So let's move on from this now. Okay, so these are like, this slide is supposed to tell you why it's important to study these particulate flows or dusty flows. So like this, oops. Yeah, I put a tsunami because in tsunami, like you don't have dust particles, but you have huge rocks and boulders, which the ocean brings and dumps on the land. So like, it's dusty flow on some humongous scale. So you can have like very bad big rocks brought in. Air pollution is a good example that we really need to work on. Which city do you guys think this is? Mumbai? Delhi? Okay. I think it's Delhi, but I can't be sure. There's the sun there if you don't mind. Yeah. And then like this is what the pollution looks like it's covering a lot of North India. So we have to start worrying about it. How many of you have heard of this Great Pacific Garbage Patch? Yeah. So you know that like the way ocean currents go, they take microplastics and bad things that we throw in the ocean and they concentrate them in certain regions. And this can be bad because whoever's putting the plastic may not be the one who suffers. Like it could go to another country and land there. So whose plastic is it is a big question. So these all are important dusty flows that we need to study. And you wanted Reynolds number, here it is. So basically, it's some velocity scale multiplied by some length scale divided by kinematic viscosity. We'll be talking about two Reynolds numbers. One is a very big Reynolds number like in this flow. So the velocity will be like 2 meters per second, 10 meters per second. The length scale will be hundreds of meters. So this itself will be like, some thousand or several hundred in the numerator. And kinematic viscosity of air is 10 to the power minus 5. So Reynolds number will be 10 to the 7, 10 to the power 8, 100 million, 1 billion, things like that in anything atmospheric. And anything like of that Reynolds number will always be turbulent. It will never be laminar. We can talk about the reasons for that later, or if you have a question. But there's another Reynolds number based on the particle. See, this particle, it doesn't know that it's living in turbulence. It is seeing only the flow right next to it. And I told you, like, the big vortex will make small vortices, and there'll be vortices up to some small size. In a cloud, for example, the typical smallest vortex is like 0.1 millimeter, which is very small. 0.1 millimeter is very small. But these particles, these water droplets are 10 micron. So how big is 10 micron compared to 0.1 millimeter? How much bigger is the smallest vortex compared to a particle? Do the calculation if you have a pen. 0.1 millimeter divided by 10 micron. Hmm? 100. Let's check. 0.1 millimeter. 1 millimeter is 10 to the minus 3 meters. So 10 to the minus 4 meters. And 10 micron is 10 to the minus 5 meters, correct? 1 micron is 10 to the minus 6. Agreed? Yeah, it's around 10 times. Okay? Huh? You took it as 1 micron. Yeah, cool. But sometimes that also happens. There are particles of all sizes. So you're not wrong I'm just making some order of magnitude estimate. And the vortices may be of all sizes also. So here is a vortex whose size is 10 to the minus 4 meter, which I've drawn very big here. So here's a rotating flow. And here is a particle which is about 1/10 of that. Okay. Now this particle, it doesn't see the rest of the turbulence. It sees only the small vortex or the small thing that it's living near. So in terms of the particle, the Reynolds number is very small. So if the particle is moving at v velocity and the flow is moving at u, then it sees only the relative flow, which can be very small. So this velocity will be very small. The particle radius A is very small. This is the particle radius A. And the Reynolds number can be small. So depending on, what kind of particle it is, the Reynolds number can be very close to 0 and the Reynolds number can be about 10,000. So particles see a very different flow. So one way to think about this is the following. Like suppose you are a bacterium. Okay, and you're living in a very turbulent flow, like I've switched on the fan and you're a bacterium like running around in a room. For you, the air around will look like a viscous honey. It will look like goo because you're smaller than the smallest vortex. So you don't see the vortex, you just see some smooth flow inside the vortex. And then, you're swimming against some very, very viscous substance. So although the viscosity is the same for everybody, like whether it's an aeroplane or a bacterium, what you feel, the relative size of the viscosity compared to the relative size of the inertia, that thing is very small for a bacterium. So there's very different physics which operate when the Reynolds number change. That's why this non-dimensional number is so important. And so here I've just drawn a thing where you see turbulent flow, like the fluid is going, air is going in all these directions and particles are getting pushed around by the air and they can also push around the air. So that's what is happening in these flows. Yeah, I told you, we can't see the thing on top here, but if we could see it, this is what it will look like. There are Schlieren images. There's also Schlieren equipment in the lab. There are Schlieren images which tell you what my plume will look like. If I show my hand in that, you can see how much turbulence is coming out of my hand right now. And so this is just a little object which is, moving in that direction. this is what it looks like. Somebody asked, what is the vorticity arranged like, right? So you can see like here, these blues are high negative vorticity, the reds are high positive. So like they're all arranged in tube-like, noodle-like things, except that they're not like a bowl of noodles, because these noodles will become stronger, become weaker, they'll be born, they'll die, they'll push each other around. So you can see how badly chaotic the whole thing is. Yeah. And turbulent flows are vertical. This is what we talked about. And if we could see turbulence, we'd see vorticity everywhere. So like if you think of turbulence, think of the adjective vertical or vorticity, or the noun vorticity. So, and we discussed that turbulence is sometimes beneficial, right? For any mixing, it's beneficial. Like you can, if you know the heat equation, you'll be learning it if you haven't already learned it. You can do this small calculation. Like suppose I take a cup of tea, and I put 1 spoon of sugar, liquid sugar, because if it's solid, that makes extra problems, at the bottom. And then I put the tea, and then I don't stir it. I put it very carefully like this. Any guess how long it will take for my tea to become sweet? I'm not allowed to stir it. Quick guesses. What? 2 minutes? 1 minute? I'm not allowed to stir it. Huh? What? Temperature will reduce? Mm. Yeah. No, the sugar is liquid form, I told you. To make life easy, I made it a liquid sugar. So then, yeah, very carefully I poured it so they're not mixed. And I'm not allowed to stir it. So when will my tea become sweet? Undisturbed. That's the rule. You can't switch on the fan. You can't do like cheating things. Huh? Tea is hot. 30 minutes. Other guesses? Okay, but like some sweet if I want on the top, like I want to sip the top. 10 minutes? Okay. Huh? Okay. Let's imagine that the density is not a problem. It's diffusing. Okay, the answer is even without density being included, it will take about 4 months. Yeah. It will take about 4 months for your tea to get sweet. Yeah, you can do this calculation on the back of an envelope. Yeah. What? The temperature will have some effect. Like if it's warmer, the diffusivity is a little more, so it's easier for sugar to mix. So the temperature does help, but obviously my tea is not going to stay hot for 4 months, right? So like after the first 30 minutes or something, I'm at room temperature. Yeah. So you need to stir it. So you need turbulence. Mm. Okay, then you're cheating. You're cheating because see, like you've got some flame, let us say. Kuch bhi. Like I've got a tea hot, okay? I've got tea hot over here, right? And then I'm putting my cup here, and here is the sugar, and here is the tea. This is cheating. You know why? Like the minute you put high temperature here, this will become lighter. And because it's lighter, it will start convecting. So I'll get convection. It's just like when water boils, you see that, no? So it's actually become turbulent. It's become unstable and turbulent. Like spoon is not the only way to make it turbulent. I can make it turbulent by heating also. Mm. Yeah, it will reduce the time a little bit. Little bit. 4 months might become 2 months. Yeah, it's still not going to be drinkable. Yeah. Okay? So, like, it turbulence is nice for mixing things. So, yeah, the point I was trying to make here is the important thing I want you to take home. The rest of the lecture, if you don't get its evening lecture, don't worry. But we till now, what are we agreeing? We're agreeing that if there's, red fluid and blue fluid, then I have turbulence, I'll get some purple fluid. If there's A and B, I'll get A and B mixed everywhere. So this is what we believe is turbulence, the role of turbulence, to mix things which are, first separate, correct? Now in this particulate flow, I'm going to show you this movie. So here is some turbulence, and let's say cloud, there's lots of droplets, or a dust storm, there's lots of dust particles, all of that. This is a movie made by Jason, just solve the flow in 2 dimensions. He is now faculty in, where did I put that? He's now faculty in IIT Bombay. So I'll just play the movie for you. See these particles, they're going out of the rotational regions. They're demixing, agree or disagree? See, they're going into some parts of the flow, whereas sugar will go everywhere. These ones started everywhere in the flow, but they're going to some positions as time goes on. The blue spots are vorticity. It's just like the blue means high curl, that's all, high magnitude of curl. So wherever it's very rotational, these particles are getting centrifuged out. So they're actually demixing and they're sitting in the strained regions. So like turbulence does to particles the opposite of what it does to sugar or some liquid. So this is the interesting thing that turbulence does. And now we talked about small particle Reynolds number. That's what these things are. And Punyakoti, she was a summer student in my group some years ago. And she brought these beautiful seeds. I have them in my office. If somebody is interested, come. And I wanted to bring one, but I forgot. So when you throw it, it comes down like a helicopter. It's really cute. So yeah, basically these are all different particles in flow. So dust means it need not just be tiny round dust particles. It could be particles which have funny shapes. It could be big boulders in the tsunami and things like that. And these are the rocks brought by tsunami. Look at the flow behind it. Behind it itself, it creates turbulence. So like the air doesn't go like this in straight lines. It goes in a very, very turbulent, it's called a wake. So this particle is moving this way and there's a wake. So Punyakoti studied these seeds with the view of understanding evolution. So it is not just fluid mech, but how fluid mech affected evolution and evolution affected how these things go. So yes. Demixing means I'm starting with a mixed situation and it's going into certain places and not others. So it's giving empty spaces and occupied spaces. So it's evacuating certain portions. That's like demixing. It's crowding into some regions and leaving some regions. Sugar will never do that, right? More questions? Particles do that. Heavy particles do that because they get centrifuged out if something is rotating. Simple reason. Yes. Would they also be demixed or? Yeah, like if you're mixing solid sugar, while it's staying solid, it will leave the vertical regions until it dissolves. Yeah, that's why it's better if you powder the sugar, or it's faster if you powder the sugar. Yeah, more questions? Yes. If the vorticity stops, the particles will move, like they'll either fall by gravity or they will come back to mixed or something like that. So if there's some, reason, some force acting on them, they'll respond to that. If there's no force, then they'll stay wherever they are. So in some situations where, the fluid dries out, then they go into these things and they stay wherever. So then they'll remain demixed forever. Yeah, more questions? Okay, let's move on. Okay, this is a nice movie made by my friend Jim McElwain, and he shared it with me when I said I want to show it to students and all. So this is about a snow avalanche. Okay, so like what you're going to watch is the following. There is a mountain. This is somewhere in Switzerland. I've written the name of that place. Okay. So these guys go there and they stay for some days. It's a mountain with snow on it. And then they have a little plane and they have a pilot who flies the plane. And that pilot carries like TNT, basically a bomb, and a small plane which will drop this bomb on the hillside. And so like here is the hill. So suppose here is the hill, he drops the bomb here, that will release the snow. So till then the snow is just sitting there, air is sitting there, there's no turbulence, nothing, it's all quiet like hillside. And then these things, and these snow is actually a powder, right? So once you get the powder out, it starts rolling down the hillside, and then it will start eroding the hill. So more and more snow will start falling, and it will become bigger and bigger, and it becomes very, very turbulent. So then they put a little tent here and they measure like what's coming. Sometimes they get buried under the snow coming, so they have to run. So they try to measure things and they try to understand like how powerful an avalanche can be, depending on the slope, depending on many things. So then they try to do calculations. So want to see the movie? It's not very clear when the pilot drops it. See there, he dropped it, he was there. You saw it? And see how much snow is coming down. See, it's coming down here, and Jim will be like one kutti dot here. It's that big, that snow avalanche. They put some towers and things and they try to measure. Want to see it again? So here the turbulence is not caused by something else. Like in a cloud, the turbulence is there and these raindrops are caught in it. But in this case, there was no turbulence, but turbulence happened because of these particles. The particles are only pushing the air and making turbulence. So that's why it's different. Okay, so like why this problem is hard. So this is the Navier-Stokes equations. I promised not many equations, but I didn't say zero equations. This is the Navier-Stokes equation which describes the fluid velocity at every place and every time. And it's just Newton's laws. But it's very complicated because, if I'm looking at Newton's laws acting on one body, then typically like there's one block and some force is acting and it's accelerating. But now this is a fluid parcel which is poorly defined, and every other fluid parcel is putting force on it. So like it's an infinite dimensional system where everybody is forcing everybody else. So if I'm a vortex, I'm going like this, that guy is going like that guy will be forcing me. So there'll be a response of me to that one. So like that. So it's a very, very complicated thing. And if you're going to solve for a cloud, you have to solve many, many more equations for dust particles, this and that. And in a cloud, like there's all of this stuff going on. It's not just turbulence, but there's planetary aggregation, evaporation, blah, 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 solar radiation. It's a very complicated problem. But the point is, like on a planetary scale, the big scale is 10,000 kilometers and the smallest particle is 1 micron. And the ratio is 10 to the power 13. So if I want to solve Newton's laws for everybody in this earth, from the smallest particle to the big cloud, then like I need 10 to the power 13 grid points. If I take a differential equation and I write so many grid points, it's impossible in today's computers, tomorrow's computers, whatever, whatever. So we can't solve it by computers. That's what makes it very, very hard. And this is only for the turbulence, let alone the how many droplets per cc. How big is a cc? Show with your hand. Centimeter cube. That much, right? There's 1,000 droplets in each of those. And the cloud can be kilometers in size. So there's quadzillion droplets, like we don't even know how many zeros. That many droplets. So, and if each droplet is doing something like turbulence behind it, it's doing its own thing, then to solve for each droplet and all is impossible. That's the message that we convey here. So like I can't make a grid which is big enough. I can't make a grid around each droplet which can solve for it. Not happening. So like we have to think of clever analytical ways or clever thought ways to solve these problems. And we have to think of how to connect simple understanding that we can get with pen and paper and all to, the big weather prediction models and all that people run. We have to put this understanding into that. So that's where the science is in our group, for example. So yeah, this is one good place to stop and I don't have to tell about the science. If you have more questions. Okay, let me continue then. I put one 12th standard thing because I thought everybody will know it. You all know this? Yeah, so every particle, if it is spherical, it's falling in a straight line downwards and it has a velocity v and there's a Stokes drag, right? How many of you have seen this? Everybody has seen it. Yeah, so this is the drag and this is the buoyancy reduced weight. So there's weight minus buoyancy minus drag. That's the net force acting on the particle and it's coming down. And in JE coaching, you'd have surely studied that this is the formula, right? You start it from rest and it in exponentially fast, it will reach the terminal velocity. How many of you studied this in JE coaching? 1, 2, 3, 4, 5. Yeah, lots of you studied it. Yeah, but the actual formula, this is actually an idealization. We did a better job like in 2019, like some years ago, and with the help of Vishal Vasan, who's a genius colleague we have in ICTS, and Ganga Prasad, who is a genius student also. So then we got this formula for V. It's not exponential in time, but it's algebraic in time. So this is a much better formula than this one. Okay, just for a particle falling. So when you just have raindrops falling, how fast they reach terminal velocity is exaggerated if you go by JE coaching. So yeah, so this result was very exciting for Beverly McKeown. Like she is a faculty member in Stanford and Tomek is her postdoc. And Divya is like our student who's now postdocing in Harvard. But when she was in ICTS, she did this work and she showed how it was slow and all. And these people, they wanted to do a little experiment to see if what we are saying is correct or not. So then we did this experiment where one tiny ball is dropped in silicone oil. So it's mimicking a small particle in a very viscous flow. Although the ball is not that small, we made it so viscous that it was small. The Reynolds number was very small. So then we showed that the terminal velocity, which is that much, is actually reached very slowly, not like that black line is JE coaching. And this one is the real one. And this experiment and Divya's theory, they match so nicely. And Divya also solved for the flow around the body. And this itself is interesting because, see, like when the body falls, it will drag the fluid with it, no? So you expect some fluid to be moving downwards. Whereas instead of moving downwards, the fluid is doing this. The ball is moving like this and the fluid is doing this. So one big vortex ring is formed. It's actually a ring we found out that it's a ring. So here's a ball and there's a vortex like this, like a bangle around it. If I cut it, it looks like this. Got it? Got it? Yeah. So there's a vortex ring around it. And experiment and theory matched very nicely. So like this is going to be important because suppose I'm a particle which is falling down and you're a particle who's standing next to me, you'll be pushed up by the fluid, which is counterintuitive. So a lot of funny behavior might happen even at very small Reynolds number. And this kind of thing is this is the last thing I'll tell you, like we'll stop with this photo. This kind of thing is very, very important for carbon sequestration. So how many of you know about plankton? Everybody, what is plankton? Tell loudly, no? There's photosynthetic microorganisms. They're the lowest part of the food chain, correct? In the ocean, right? So they live in the ocean. And do you know where they live in the ocean? What? Yeah, sometimes in those where the currents are, like where there's a temperature gradient, they live in that. Yeah. So, but typically they live in the top part of the ocean. So like what happens is these are photosynthetic, you said, no? So by definition, they need light. If I go a few meters down in the ocean, it gets very dark. So like if I depend on photosynthesis, I can't live there. So I have to live somewhere near the top. But then like if I live very much near the top where it's very bright and I'll happily do photosynthesis, there's no nutrient for me to eat. The nitrates and things are more in the bottom, ocean bottom. So like, I have to do a compromise. So like, the nitrates will keep increasing as I go down and it will be zero on top. And the light will be good on top and zero below. So like I will live in a middle place, like some maybe 2-3 meters below the ocean surface, not very deep, less than a swimming pool. I live in that place where sunlight is miserable and food is miserable, but neither of them is zero. So I live in that place, right? So that's where these guys live. They live in the ocean in one almost like a 2D surface on the ocean. And satellites can pick it up because the whole ocean color changes. So satellites can measure how much it is. So why do we care? Like, why are satellites wasting time and money measuring them? Oxygen production is one thing. It's not very like a very big contributor to oxygen production, but I may be wrong. Yeah, what were you saying? Why do we care about this? Okay, so the answer is given here, carbon sequestration. And I'll tell you what that is in a minute. So like I put this little creature, this little plankton, and I showed where its shoulders are because like one of my oceanographer friends, he said this in a very nice way. He said, on these people's tiny shoulders lies the responsibility of reducing carbon in the atmosphere. So we guys are the bad guys who keep putting carbon in the atmosphere and then it results in global warming. So these pavam little things, they actually like suck up more, they suck up human-made carbon, 30% of it. So they help in climate change mitigation. So then they suck up the carbon and then like as they die and all, they fall into the ocean, and how they fall, it's very important to know. And so like then other things eat them and they're like, so the carbon gets taken to the lower ocean. And the more the carbon gets taken down, the more carbon can get absorbed. So in fact, one of the geoengineering solutions, a big important geoengineering solution that people are thinking about is to grow lots of plankton, is to farm plankton all over the ocean. So that like we'll keep doing the bad things we do and then the plankton can take care of the rest. So this is one thing. So maybe I'll stop here because it's almost 7 o'clock. I'll go to the end of the last one. There's some nice movies of particles falling and all, which I can't show, some cloud things. And this is my group, okay? These people are the reason why I stand here and give bhashan. So this is the conclusions. I'll leave it here. I want like many people in this room to study these important subjects in their life. Thank you. Questions?
So since they're taking a large amount of carbon down, will it be helpful in generation of any kind of fossil fuels?
Yeah, so over millennia, it will create fossil fuel. Over some millennia, like the more carbon that goes down, the more fossil fuel, which is good or bad, we don't know.
And can we explain the generation of the fossil fuel that is already there due to any of this?
So the fossil fuel that's already there is because of carbonaceous matter like trees or any living things which have gone in and lived under high pressure and got converted to fuel, right? So yeah, like all of these living things only create fossil fuel.
Thank you.
Anybody else? Can somebody?
Hello. Ma'am, you mentioned the carbon sequestration, right? What's the role of turbulence in that?
So, like, it's not very clear what the role of turbulence is, whether it slows it down or speeds it up. But basically, like, will it accelerate the sedimentation or not? And usually it accelerates because turbulence helps in making clumps. And if it's a bigger clump, it will fall faster. So like, yeah, there are people who actually measure like the rates of falling. What they'll do is they'll put one long rope in the ocean with many cups at different depths. And they will come back after 2-3 weeks and with the ship and they'll pull the cups back and they'll see how much was at which depth. So they can actually measure these things as a function of height and time. So yeah, like there are many reasons for it, and I don't think it's a solved problem. It's not an understood problem. In fact, like we are planning some big experiments where we'll put balloons in different parts of India to understand. But so depending on the wind direction and the rate at which, see, these particles are heavier than air, so they're actually falling. But because they're very small, their terminal velocity is very small. So they're falling slowly when there's turbulent air. So now it depends on how much turbulence there is, how much wind direction, where the wind direction is at a given time. And you're quite right that every city has pockets of pollution. Like Bangalore is a pocket of pollution. But like how it diffuses, we don't know how it diffuses into the rest. And then like there can be, let's say, desert sand. It can be coming from Arabia also, we don't know. So like depending on the wind direction, it may be coming from place A and going to place B. So there's a collection of pollutants, then industrial waste, then crop burning, and then actual dust and sand. So all of these together make up the particulate matter. So we don't know like what is really causing it and how to address it. Yeah, so some of these things are very not intuitive and not easy to explain. People say crop burning is a big issue, but I don't know like what fraction of this is crop burning. Yeah, but if it's locally burned, then locally you're going to feel it more. It may take weeks for the wind to take it away, and by the time it would have fallen, it would have hit the ground. Yeah, these are all sinking matter. Cyclone is diverted. Okay, so the point is, like, it's got diverted means what? Like, compared to you want it to move in a straight line and it didn't move in a straight line, or you made a prediction and it didn't obey your prediction. So that's what we mean by diverted, but that's because we couldn't solve the equations correctly. I told you, no, it's very hard to solve that equation. So we solve the equation by some model, and the model tells that this is the cyclone track, but the real cyclone track is somewhere else. If we could solve it correctly, we'd get the correct track. There's no reason why we can't get the correct track if we solve it correctly. So that's what I'm saying. So suppose this is land, okay? And the cyclone is coming from something like this. And like it's reached here at some day, and then you're extrapolating. You're drawing a line and you're saying it hit here. But actually it hit here. Correct? So what I'm saying is it didn't get diverted. I solved it wrong. I couldn't solve the equation, so I got a wrong prediction. And that's the best we can do because computers are only that powerful.
Ma'am, how does inertia play a role in our understanding of turbulence, or what is the T?
So basically, like, I mean, it's only a thumb rule. There's lots of ins and outs, lots of things. But basically, the less viscous the flow is, or the more inertial, means it's faster and bigger, then it's more likely to be turbulent. And there are like reasons for it, which you can understand if you take the whole flow, do a stability analysis, see what is stable, what is unstable, and why is turbulence an attractor. Somebody here talked about chaos. It's actually a chaotic attractor. So you can actually do the maths to work out some of these things. For certain flows, some easy flows, you can do it. So it's not an easy question to answer, but the maths will show you how it becomes turbulent.
Ma'am, what do you mean by an attractor?
Attractor means like it's a solution of the Navier-Stokes. So like this Newton's laws I told you are called Navier-Stokes equations, right? They don't have unique solutions. They have many solutions which are possible. So which solution will the fluid choose? That I'll call as an attractor.
How can we decide which solution the fluid would choose?
We can't decide it. We have to see like by the physics which it chooses in a given situation. Thanks for your attention, guys.